Section E. Data and Information Management and Solution Development. Question 7. To manage their day-to-day business operations, Fairly Fit have many IT solutions using both database and OPP designed applications. 7.1. Data stored or transmitted across a network can often be subject to threats. Consider a database which Fairly Fit use to store details of their gym and cafe customers. 7.1.1. Explain what each of the following threats to quality data means and give a possible example of how customer data could be affected in the Fairly Fit database. The first one, outdated data. Definition. Outdated data refers to data that is no longer accurate or relevant due to passage of time. Now this should be highlighted. That's the definition. This can occur where data is not regularly updated or maintained, leading to a mismatch between the current situation and the data stored in the database. An example, a customer's membership status is listed as active in the database, but they actually cancelled their membership 6 months ago. If the data is not updated, Fairly Fit may continue to send them promotional offers and membership renewals, leading to confusion and potential loss of trust or annoyance. IEB's memo's answer gives this definition. This is where data stored in the database is no longer valid. The actual field values have been changed but have not been updated in the database. Example, customer has changed their phone number, but this has not been changed in the database. The value of the phone number in the field is out of date. Invalidated data. Invalidated data refers to data that fails to meet the required criteria or standard for its intended use. In the context of Fairly Fit's database, which stores details of their gym and cafe customers, invalidated data could manifest in incorrect formatting. Suppose the database requires phone numbers to be stored in a specific format. For example, 123 in brackets and then 456, then dash 7890, close brackets. If a customer enters their phone number as 123456780 without the required formatting, this invalidated data might cause issues in communication or system integrations. The second point is incomplete data. If a customer profile is missing crucial information such as required email addresses or membership start date, it could lead to problems with customer management, such as difficulties in sending promotional emails or tracking membership renewal date. The third point is entry data errors. If a user enters non-numeric value where the system expects a numeric input, for example, entering a non-applicable for a membership ID status, this could disrupt queries and reports that rely on numeric values. Now, IEB's answer on invalidated data states that this is where data is being entered into the database, but the data which is entered does not pass a validation process. For example, a customer's ID number is being entered and it does not contain the correct number of digits. Customers using the Fairly Fit website need to first log in. A hacker is attempting to log into the website and steal customer information. All information about every customer is stored in a table called TBL customers. The hacker has made up a customer ID, Harry0209, and type in the following line into customer ID field on the web page. Select star from TBL customers, where customer ID equal Harry0209 or 1 is equal to 1, semicolon. Letter A. Entering an SQL statement into a web page field is a malicious SQL technique. What name is given to this technique? The answer there is SQL injection. Letter B. Explain what this line of SQL code will achieve. The answer is this. The SQL statement selects star, which means everything, so selects everything from TBL customers, where customer ID is equal to Harry0209 or 1 is equal to 1. This is designed to bypass the login check. The condition or 1 is equal to 1 always evaluates to true, which means the query will return all records from the TBL table, potentially exposing all customer information. Original query. The query aims to select all columns, which is the star, from the TBL customer table where the customer ID matches Harry0209. The specific technique used here is called a Boolean-based blind SQL injection attack and is a clever trick used by the hacker to bypass the authentication mechanism. By making the SQL query always true, the hacker can access all customer data without needing to know a valid customer ID. Now, I implore you, you will find a link in the description of this video which will take you to the most popular video on this topic, SQL injections. Once you watch the extremely engaging video by Network Chuck, you will finally understand how SQL injections work. And you'll be given an exercise at the end of that video, which again, I suggest you try out. The exercise was initially suggested by him, which was tried by yours truly. And I assure you, I feel proud after taking that exercise. Because of this, I suggest that you take the exercise as well to improve your understanding of SQL injections and do it yourself. That way, you will understand just how thrilling IT can be. In fact, this is me signing out on answering the rest of question 7.1.2, because every single thing is answered in that video. Just make sure you come back though, okay? Now then, 7.2. IP addresses are stored in a fixed number of bits. An IPv6 IP address consists of 8 16-bit fields, each separated by a colon. Each 16-bit field has 4 hexadecimal characters, each using 4 bits. Here is an example of a valid IPv6 address. 2001:0000:0000:FF00:0042:8329. Alternating 16-bit fields are shown in different colors for clarity. Now, before we start 7.2.1, this could potentially raise the question to some of you curious but lazy folks out there. What happened to all the previous version of IP, and why are we only using IPv4 and IPv6? What happened to IPv1, 2, 3, 5, 7, 8, and 9? Here is your answer. IPv1. IPv1 was not publicly used. The first version of IP, which was introduced in 1974, had an 8-bit address size. It was not publicly used and was very soon replaced by IPv2. IPv2 was experimental. It was introduced in 1977. IPv2 had a 16-bit address size. It was experimental and never widely adopted. IPv3. IPv3 was not publicly used. IPv3 was skipped to avoid confusion with the Internet Protocol version 3, IPv3, used in the Internet Stream Protocol, ST. IPv4, current but being phased out. Introduced in 1983. IPv4 has a 32-bit address size, allowing for approximately 4.3 billion unique addresses. It is still widely used, but is being replaced by IPv6 due to address exhaustion. Now, IPv5 was experimental. It was introduced in 1979. IPv5 was an experimental protocol that used a 32-bit address size. It was never widely adopted and was eventually replaced with IPv6. Now, IPv6, which is current. IPv6 has a 128-bit address size, allowing for an almost unlimited amount of unique addresses. It is designed to replace IPv4 and provide a much larger address space. IPv7, not assigned. There is no IPv7 protocol. IPv8, not assigned. There is no IPv8 protocol. Now, IPv9. IPv9 is experimental. It was introduced in 1992. IPv9 is an experimental protocol that uses a 64-bit address size. It is not widely adopted and is not intended to replace IPv6. Note that only IPv4 and IPv6 are widely used and recognized as the standard Internet protocols. The others were either experimental, never adopted, or skipped to avoid confusion. Because these are highlighted, we shall now go into the intricate details of these two addresses. IPv4, Internet Protocol version 4. Address format. IPv4 addresses are 32 bits long, typically represented as 4 decimal numbers separated by periods, dotted decimal format. Each number ranges from 0 to 255. For example, 129.168.1.1. Structure. 32-bit addresses. This gives a total of 2 to the power of 36 unique addresses, which is about 4.3 billion. Subnetting. IPv4 addresses are often divided into network and host portions using subnet masks. Limitations. Address exhaustion. The rapid growth of the internet has led to IPv4 address exhaustion, where the available addresses are not enough for the increasing number of devices. Special address ranges. Private addresses. For use within local networks, for example, 129.168.0.0. This can be ranged to 129 period 168 period 255 period 255. Loop back addresses 127 period 0 period 0 period 1 for internal testing on local machine. Next, IPv6. Address format. IPv6 addresses are 128 bits long, represented as 8 groups of 4 hexadecimal digits separated by colons. For example, I'm not going to say that. Structure, 128-bit address. This provides a vastly larger address space of 2 to the power 128, about 340 undecillion unique addresses. The second point, simplified header. IPv6 has a simplified packet header compared to IPv4, which improves routing efficiency. Third point, features. Address auto-configuration. Devices can automatically configure their own IP addresses using stateless address auto-configuration, SLAAC. Improved security. IPv6 includes IPsec, Internet Protocol Security, as a fundamental part of the protocol suite, providing better security for communications. No need for NAT. With a larger address base, IPv6 eliminates the need for network address translation, which was commonly used in IPv4 to manage address shortages. Address types. Unicast identifies a single network interface. Multicast identifies multiple interfaces, a group of devices. Anycast identifies a group of interfaces but sends data to the nearest one. Address notations. Zero compression. Consecutive sections of zeros can be replaced with colon, colon. For example, I am not going to say that. Next one. Leading zeros. Leading zeros can be omitted within each 16-bit block. For example, you are given the example. Transition and coexistence. Since IPv4 and IPv6 are not directly compatible, transitions from IPv4 to IPv6 has been a gradual process involving dual stack, running both IPv4 and IPv6 protocols simultaneously. Tunneling, encapsulating IPv6 packets within IPv4 packets to traverse IPv4-only networks. Translation, converting between IPv4 and IPv6 addresses where necessary. IPv6 adoption is increasing as the need for more addresses grows and as the limitation of IPv4 become more pronounced. Now then, question 7.2.1. How many bits will be required to store one IPv6 address? The answer is quite simple. 16 times 8. Because there are 8 16-bit fields, we multiply 16 by 8, which gives us 128 bits. 7.2.2. IPv6 addresses are long and difficult to work with, so several techniques as we have discussed, are being used to shorten an IPv6 address without losing its uniqueness. One way of achieving this is by removing leading zeros, ensuring at least one character remains in each of the 16-bit fields. Applying this technique to the IP address shown above, we would end up with the following address: 20.0.0.0.0.ff00.ff00.42.8329. Now, considering the following IPv6 address, I'm not gonna read that. Once again, the alternating 16-bit fields have been shown in different colors for clarity. A. Write out this IPv6 address in shortened format using the technique described above. The first two fields are shown for you. The answer is this. Letter B. Assume that because we have a shorter IPv6 address, we can use fewer bits to store the address. Use the table or grid below to work out how many bits will be needed to store the shortened IPv6 address from A above. The first two blocks have been filled in for you. Now pause the video and try to solve this answer using logic. Here is the answer. Letter C. The shortening technique used above suppresses leading zeros. Why is it not possible to remove trailing zeros as well? Use the field FF00 to assist in answering this question if necessary. Create an answer.